You can hear me?
Okay.
Yeah, we can hear you.
Okay, thank you.
Great. Well, welcome to our first Geometry Multi-Series seminar of the new year. Our first speaker today is the McMaster, Siegfried from Hille, and he's going to tell us about parametrizations.
All right, thank you. So first, thanks for letting me speak in this seminar. And then I will start with a quick disclaimer. So the first talk on a Blackboard I will be giving in a few years. So we will see how that goes. So the goal of my talk is not necessarily to talk about something new, but it's more to explain the relation between the Hille-Wilke theorem, which is a big result in O-minimality and number theory, and how it inspired a lot of research on parametrizations. And so these parametrizations, they have a lot of, in the requirement, in the statement, you'll find uniformity requirements. And the goal of the seminar is to explain why these are there. So I hope it's not too technical, but it kind of is. And I'll try to skip all the other details of the Hille-Wilke theorem. All right, so let me start with some notation. For the people online, I'm not sure how readable everything on the Blackboard is. So if I have to write a little bit bigger, let me know. So in my talk, usually I'll consider a set X in Rn. The dimension of X, real dimension, is M. All right, that's it for now. So I will start with the Hille-Wilke theorem. So I have to introduce some number theoretic notions. So first we will define height.
So dimension is what?
It's just a real topological dimension.
Okay. Topological.
Okay. So if you have a fraction, a rational number, and so I assume that A and B are co-prime, then its height, which I denote by a small h, just the maximum of the absolute values. And then you can extend this notion to tuples of rational numbers by just taking the maximum over all rational numbers in your tuple. And so then we can, using this notion of height, we can define the following set. So it's the set of rational points on X up to a certain threshold. So H is just a natural number. It's a bound on the height. So this set is all points, rational points on X that have bounded height. So the height of this rational point is at most some H. So the Hille-Wilke theorem will make a certain statement about this set. First, what are definitions? So the algebraic part of a set. So we denote it X alg. So this is just a union of all semi-algebraic sets contained in X of dimension at least 1. And then we are going to remove this set actually. So you take the transcendental part of X, which is just X without X alg. And so actually this transcendental part is what the statement is about. Good, so the Hille-Wilke theorem then. So given any positive epsilon and the definable set X, And definable means a no minimal structure. Well, here it can be arbitrary, so let me. So then there exists a constant C. And let's see, such that for any H, you can bound the rational points on the transcendental part of X. In this way. So you see, considering epsilon as a small number, this actually means that up to some constant that depends on epsilon, you can force the growth in terms of H to be, well, lower than any power H if you want. So sometimes we call this subpolynomial growth. And so the reason that we are looking at the transcendental part is because in the algebraic part, for example, think of a line can have many rational points, or something like h squared or higher dimensions, even more. Okay, so this proof, well, the proof of this theorem, you can do this. Well, the original proof is by induction on the dimension of the set. More recently, there's also a proof by Lau and Nier. Not gonna try to pronounce your last name. I'm sorry, Nier. But they have also a new proof, and it's also, I think, a more readable and a very nice proof. So I definitely recommend reading their paper if you want to prove or look at another proof of this theorem. It's a really good proof. And I'll be discussing the usual proof, and actually the role of parametrizations doesn't really change so much. So from that point of view, it doesn't really matter which proof you study. Or maybe. Okay, so how do you prove this theorem? So the theorem, the classical proof or the original proof by Hille and Wilke goes by induction on the dimension. So it's induction on M. So recall that is the dimension of X. So the induction, well, the base case, if M is 0, this follows by O minimality. Right, because O minimality, if X is definable and 0 dimensional, is just a finite union of points. And so you immediately just get a constant C without h to the power epsilon. So there's nothing that you have to do. Okay, so then the rest of the proof, roughly speaking, goes as follows. So to decrease the dimension, you're going to intersect with algebraic hypersurfaces. So I'm just for the talk, I'm just pretend that the dimension automatically drops if you do this. That's of course not the case, but my goal is not to give a precise proof of the theorem. I want to get to parametrization. So you intersect with a hypersurface, and I just assume that the dimension then turns to be m-1, and then you use induction to conclude the proof. So of course, intersect with algebraic hypersurfaces. Something to keep in mind is, of course, should have added to it, such that all points, well, rational points, of course, lie on at least one of these hypersurfaces. Rational points lie at least one. All right, so you have a bunch finitely many rational points. And the set here is always finite because there are just finitely many rational points if you bound the height in this way. And so each of them has to be on at least one hypersurface. And so one point is, how do you do this? And secondly, of course, you don't want to use many of them. For example, if the amount of hypersurfaces increases faster than this, well, then there is no hope to prove this theorem. Right, because we are going to use the induction hypothesis to each of these intersections. So if you have many intersections, this doesn't work. All right, so how do you do this? Well, to find these hypersurfaces, you do some basic linear algebra. So consider, for example, an equation. I'm just going to put degree 2 and dimension 2. So a hypersurface is given by this equation. All right, so in this case, you have 6 variables in 2 indeterminates. And so my point is, if you have a rational point, so for x and y, you substitute 2 rational numbers, then you get a linear equation in the unknowns, the AIs. Okay, so you get a bunch actually. So the condition that a rational point lies on a hypersurface just determines a linear relation in the coefficients of this hypersurface. And so this is one very important part of the proof, so that the coefficients of this hypersurface are determined by these rational points. So let's see, what else do I have to say? Well, also notice that it is a homogeneous system. So, right, it's a homogeneous system. So what we want to do is you just take many equations and you want to prove that the determinants of maximal rank are all 0. They all vanish. I'm not going to prove that because that's a technical point. So I'm going to give a condition under which this happens. And so that's called the determinant method that was developed in '89 by Bombiri and Hille. So let me, well, I'm not going to write a precise statement. So 89 by Bombiri, Hille. So this is not a precise statement that I'm going to write down. Maybe I'll write ID. So given D large enough, so D is the degree of your hypersurface. So large enough, that means in terms of epsilon. So this epsilon as in the Hille-Wilkie theorem, and then some combinatorial information about the set X. So in this case, just the dimension of X and the ambient dimension. So in some sense, this D is totally independent from H. So given D large enough, and well, if the rational points are close enough, then such a hypersurface exists. So for the specialists, I know which theorem I'm referring to. The point is, of course, close enough. And so that also means that, of course, if your X is a certain set, that means that if your rational points have to be close enough, that also means that you're going to need many hypersurfaces. So many, of course, means you can force it to be this many, such that you can use induction. So what is close enough in this setting? So close enough, and there might be a weird condition or weird way to write it in this way, but that means they lie in the image of a certain map phi, where phi is a map from the unit cube to X. Let's see, and all derivatives up to order R for some R are bounded by 1 in absolute value. Okay, so close enough means somehow that you're in a chart of something. Right? You lie in the image of a certain map. That's what it means in this setting, or to apply the actual result of Bombira and Hille. What you want is that these points lie in the image of a very nice map. Right? So it has derivatives bounded up to order R. So what is important for the talk, right? After this, I will state the parameterization theorem. That's what the talk is about. What is important, so again, that is that this degree of your hypersurface only depends on epsilon, m, and n. That's all fixed in the beginning. And here there is, well, I should write for some R. So I can be more precise about this R, what it actually is, when you know D. Did I write it down? Maybe on my next notes. No, well, I can tell you anyway. So R, I think, is a polynomial in D. And the polynomial, I think, also depends on X. No. There's this one. No, I don't think here it depends. It doesn't depend on that. Yeah. So in turn, R itself also just depends on epsilon, m, and n. Okay. So that's something that just comes out of this result that's proved by Bombira and Hille. You get some R, and D has to be large enough. Your points have to be close. So that's this weird condition where they lie in the image of a certain nice map, and then it all works out. Okay, now it gets tricky. We have to write the parameterization theorem. I think I'm just going to erase this. Are there maybe questions up till now? Okay, so how do you arrange this close enough condition? So this is actually the main result of the paper by Hille and Wilkie, is a CR parametrization. So that's also Hille and Wilkie in the same paper. And this parameterization result is actually was really not available when Bombiri and Hille were doing similar, solving similar problems. So what does it say? So I'm going to write a uniform version, but you can ignore the parameters for now. So let X be a definable family. So you can ignore family for now. So ignoring family means there is no T and no R to the power K. So definable still means in an O minimal structure. So then for any R, in particular the R that we need for our hypersurfaces, there is a constant C. And definable families of maps. Again, for the non-uniform version, just there are maps. Such that for any T, so for any parameter, or again, if there is no parameters, then this is not a T. So you can write X as a union of images of such maps. That's basically what it says. And so X is the union of such maps. Of course, I didn't put the conditions on the map yet. So where phi I T has derivatives at most one in absolute value up to order R. Okay, so this is what you want.
The phi's are from the unit cube.
Sorry?
The phi's are from the unit cube.
Yes.
Right.
So phi. Okay. That's a good comment. All right, so why do you need this uniformity in this statement? All right, so I said, don't pretend that there is uniformity, but this is actually very important to prove the theorem. So why is that? So recall that our proof strategy is, well, we intersect with a hypersurface. So now we can use this parametrization result, and then you intersect with a hypersurface. So but then in the next step, I have a lot of intersections. And so I have told you that if you look here at our linear algebra problem, the coefficients will depend on the height of the rational points. So let me give a very silly example of height of rational points where this goes wrong. I mean, it's just, the main problem is the following. For example, if the point 0h lies on just a line, well, then you know that A2 is equal to H, right? So it's a very simple computation, but so these coefficients can depend on H in a rather bad way. And so that means that your intersection depends on H. And so that's where you get into trouble, because if you apply the theorem, it says, well, there is some constant amount C that allows you to cover your set, but the C depends on the set. So maybe I should, it's important for my talk, so I should have made this more precise. So this C here depends on the following data. So C depends in the uniform version just on the family as a whole, and also on R. So why on R? Well, you can imagine that if you want to bound higher order derivatives, that you will have to do more effort. So more effort here translates to you need more maps. And of course, it depends on the set that you are making. Some sets are easier than others. But so my point is that it depends on the set that you are parameterizing. And so if I look at an intersection, now the intersection depends on H, or has a dependence on H. So therefore, if you parameterize it, it now introduces a constant C that will depend on H. And so that is something that you want to solve. And so that's why you need the uniformity in the parameterization theorem. So let me make that a little bit more precise. So the solution, that's why you need to prove a uniform version. So the conclusion from this example is that intersections depend on H. Intersections. So what is a solution? Well, we are going to consider these coefficients. So these fixed in advance. So you have a fixed amount of coefficients. I'm just going to consider them as parameters. So I can intersect with any hypersurface, and its intersection will depend on these parameters. And so we are going to put T as in the statement of the parameterization theorem to be hypersurfaces of degree at most D. So you can make this definable in an O-minimal structure. And so xt, in our case, to apply the theorem, is then, well, you just, is x intersected with t for every t in T. I guess that's not how I've written the theorem. So how do I write it as in the theorem? It is T and X, T and X in X intersected with T. That roughly makes sense, right? So T is a hypersurface, and so I can look at the intersection on the hypersurface. Although I would agree that it's not a perfect notation, I hope it makes sense. So you consider a hypersurface, so these coefficients. So I'm interchanging the both here, but so I want that X lies on the intersection of my original set with this hypersurface that I picked before. And so I just consider this as a big family. So you should just think of my original set X intersected with a hypersurface determined by some coefficients. And so now what my theorem says, so this is a definable family. And so the remarkable point about this theorem is that you can, well, parameterize families, and the number of charts doesn't depend, well, does only depend on the family, but not on a specific member. So that means that our problem, namely the fact that these coefficients depend on H, but we can find some C that will not depend on H because it works for all members of the family. So then you can continue. So that's why in the CR parameterization theorem, how you eliminate the dependence on H by just proving it uniformly. Questions about this? Or comments? I don't see it. No, that's the mouse of the computer, I think. All right. Which blackboard do I have? I'm going to use the Hille one. So that roughly ends the story for the Hille theorem. So the main ingredient, again, of this article is actually this CR parameterization result. So now in the same article, you get a conjecture by Wilkie. And to write this conjecture, I don't have to do so much. So let's see, give an epsilon. Yeah, I don't need an epsilon. So you don't need this for Wilkie's conjecture. Now definable will be in a specific O-minimal structure. So this minimal structure will be Rx, which in my abstract I defined as exponential algebraic sets. So these are just sets that you can define using the exponential and polynomials and using inequalities and equalities. And then the conjecture is that you can improve this upper bound, namely, well, so there exist two constants in this case, a C1 and a C2. And then you get as an upper bound polynomial in log h. Well, what I mean is log h to the power of C2. That's what I mean. So a polynomial in log h. Okay. So just a little bit later, actually, if you look at this method that Hille and Bombiri developed in 1989, you can just adapt this a little bit, and you could get the result that you want here. But it doesn't work that straightforwardly. And so the subtleties there is the next thing of the talk. So the weird thing here is that you take a degree for your hypersurfaces that is completely independent of h. And so that is what we are going to change now. We are going to let it depend on h. But you should know that many things on the blackboard at the moment depend on d. And so that's where it all becomes a little bit of a mess. And so that's, I hope to make this clear, what should be changed in order to, well, what parameterization theorem would you need to prove Wilke's conjecture if you apply a similar strategy? Okay, so let's look at what we need to do. So the idea is that we are going to set D is not anymore large enough in terms of epsilon, m, and n. We are going to put D polynomial in log h. Okay. Then you see a first problem here, because in my parametrization theorem, R is a polynomial in D. So this is a first problem. So if D is a polynomial in log h, so then my R depends on log h, also polynomially, that's okay. But here you see my constant C in my parametrization theorem depends on R. So I should not have taken red here. But so R is now polynomial in log h. So therefore, if you want your induction to work, your C now depends on h. So C, well, this has to be polynomial in log h in the end to make the induction work. So to show, I have another blackboard. Huh? Oh, no, I don't. Maybe here. Ah. So to show, you still have one blackboard left. Still. So to show is that the C in the parameterization theorem well, that it's again, well, that it depends polynomially on R. That's something that you will want to prove. C in parameterization is polynomial in R. That would be something you have to show. And then secondly, well, if D was fixed in advance, well, so our space T here that make the uniformity works. T, I defined it here, it was the set of hypersurfaces of degree at most D. So now this depends on H. And so H is just an arbitrary number, so this you cannot use this anymore. So instead, you will have to manually prove that if you intersect X with a hypersurface of a certain degree, that you can do this with a number of charts that, well, in such a way that you can just continue your proof by induction. So that means also polynomially indeed. Where are my notes? Page 4. Yeah, so you also have to do something about the uniformity in intersections. Okay, so then I will use the other blackboard. And so if you wrap up all of this discussion, you can wrap this up in a conjecture by Hille in 2010. Although I would say my version of it. So that is the following. Suppose X is definable in Rx. And then there exist constants C1 and C2 such that any intersection of X with a hypersurface of degree at most D can be parameterized, well, or has a CR parametrization with C1 poly in D to the power C2 many charts or maps. So instead of proving it uniformly, well, you basically just put the desired property in the state. So if I find the time for it, but so as a remark, this is not what's in the paper. Originally, this is stated in terms of mild parametrization. Okay. So that ends the story about the Hille-Wilkie theorem and parametrization. So ideally, we show this conjecture, which I think in this formulation is still open today. So we don't know this kind of result. But we are very close, I guess, or have found another solution to deal with it that also works. So other questions about this story? I think that's the main part that I definitely, hopefully, want to make clear is how, well, so why do you want to parameterize intersections? Why is it polynomial in D? Yeah, that are the kind of questions that you hopefully understood after this talk. The precise statement and so on is not that important, or how the proof works. It's more about all the constants. So if there are no other questions, then I'll state some results about parametrization theorems that are available now, and all the results. Let's see, are you still on this book? So let me state some results now purely about parametrization. So the first result, I think, is from 87 by Yomdin and also work of Romo. In the case that X is semi-algebraic And so it's also from 87. So the motivation was not the Hille theorem. So this is actually inspired by dynamics. And some other developments have been in that field as well, using better parameterizations. But so at that time, that was for a long time, I think, the only widely applicable result. And then the next result, at least to my knowledge, is just the Hille theorem. But this one holds in very big generality. So this holds in any O minimal structure and is uniform. So any So of course, from some point of view, O minimality is the generalization of semi-algebraic geometry. And so it's not so surprising that it is possible to prove this result using similar techniques. Although in the paper, you have to do a lot of work to get the uniformity done as well. Now, regardless to say, so this one is uniform, but it doesn't have any information on its dependence on R. So right, the first step, if you would like to prove Wilke's conjecture using this setup, is that you need to prove that the constant C in the theorem depends polynomially on R. So in these statements, there is no information on how it depends on R. So I think, how much time do I have? Not so much. So I'm gonna skip some details. I think in this case, if you follow the original proof of Yondin and Gromov, you would get exponential, at least exponential dependence on R. So you have to use other techniques to deal with this. And so these are available nowadays, so recent results, very recent. This is purely for CR parametrizations. There are some other in between for these mild parametrizations, but for CR parametrizations, we have a paper that appeared in 2016 on archive. So I'm using the archive dates now, because otherwise chronologically they're going to switch around. You have a result by my PhD advisor Raf Kluckers, together with Hille and Wilke. For X in a structure which they call power subanalytic, or just think about subanalytic sets if you want. And so they achieve polynomial in R. And then a few years later, in 19, again on archive, if I remember correctly, you have Bignamini and Novikov. Bignamini. For subanalytic. So they have R to the power dimension of X. And also they actually show, I think, this result. Namely, that if you intersect with hypersurface of degree at most D, that you can do it polynomial in D. The point is that if you want this extra feature, X has to be semi-algebraic. So plus conjecture, let's say, if X semi-algebraic. Which is a very strong result. They have to do a lot of extra work to prove this. But in the end, we are going to remove semi-algebraic sets. So it's definitely a good step forward, but not quite a conjecture yet. So, but they recently got around this. But I don't think I'll get there. So I think what I will talk about for the remainder of this talk is the mild parametrization. So what is mild parametrization? So mild parametrization, I think, was just introduced in some way to get rid of the dependence on R. So instead of bounding derivatives up to order R, you're just going to bound all derivatives in a suitable way. So definition, a smooth function is mild if there exists three constants in P and C, such that so this so you have this growth condition on the derivatives of a map phi. So maybe I should a smooth function phi is mild. You have this for any multi-index new, let's say, in our case, m variables, the dimension of the set that you want to parameterize. And so in a certain way, you recognize this bound. If C is 0, you almost get analytic. But the point is that the analyticity doesn't depend on the point that you're looking at. So it's kind of uniform analytics, what I sometimes tend to call it. Or you have so this for any x maybe. So it's a similar bound for analytic functions, but you slightly relax this dependence on the factorial by adding a constant c. So in a certain way, this avoids your dependence on R. But it turns out that well, mild parameterization, so you just want what is mild parameterization. So you want the same statement, instead of derivatives at most R, at most 1 at 2 order R, you replace this with mild. And the constant C, of course, is again doesn't depend on parameters, so you want it to be uniform. But this turns out to be very hard. So in fact, there are negative answers. So a result or an example by Yondin shows no uniformity if C is 0. And then we have a result by Thomas that also shows that there are O minimal structures that don't have mild parameterization in the way I just mentioned. So there are O minimal structures without mild parameterization. So that means there is some sets in there that do not admit such a parameterization. All right. Where do I have some space left? Maybe I'll write it here. So I'll finish with 2 positive results for mild parameterization.
The derivative, the coordinate.
Yeah, this is the
Okay,
derivative with respect to a certain multi-index. Yeah.
this one.
Not sure. So positive results. Oh, what do we know? In the same paper by Bignamini and Novikov, you have 2 mild parameterization, where 2 means that the C, the constant C, which is in fact the most important growth rate in this upper bound is 2. Right. And then you have a result by myself, I think 21, 22. I think 22 is the publication date. Well, I'm doing archive days. Let's put 21. So you can also do this in the, I follow the result by Klucker, Spila, and Wilkie. So you can do 1 plus epsilon mild for X in this so-called power sub-analytic setting. And if you furthermore assume that the dimension of X, the family, is 1, then you can actually do epsilon mild. And so epsilon is, well, arbitrarily close to 0. But that only works for dimension 1. So in some way you can get, so by this example of Yomding, we know that you cannot get C equal to 0. I've shown that you can get arbitrarily close just for curves. But I do want to say that these results in the end, so in some way you eliminate the dependence on R, but you see this upper bound is not exactly bounded by 1. So in the end, you have to do something or something equivalent such that it is bounded by 1. And so in the end, if you really count how many charts or maps that you will need or end up with, the mild parameterization, well, they are equivalent. But for example, if you have 2 mild, it's not better than having this underbound. This bound that Bignamini and Novikov have, or to the dimension of X, is roughly the best you can get. And so the 2 mild is slightly worse than that. And even 1 plus epsilon mild still does. Somehow you have to get 0 mild to get a similar bound, which you can't. So just going through smooth functions doesn't work as good. I mean, to obtain the proof of the theorem, it's just fine, but you see that the theory is not as nice. It's also more complicated. There are other issues with this parameterization that I haven't addressed. So yeah, mild parameterizations, they are the same, but they're harder to construct. And so yeah, I think might not be worth studying anymore from this point of view, but who knows? Yeah, so last thing that I will say, to address this problem with mild parameterizations, people still hope to find a 0 mild, well, C0 mild parameterizations uniformly. And to do this is somehow you exclude a region around the singularity. So singularities introduce problems. Somehow if you stay away from these singularities, then you can achieve uniform 0 mild parameterizations. And so there is also work on that by, for example, my supervisor. But yeah, I'll stop here. Thank you.
Thank you very much. And are there any questions? So I just remind me about in general, these maps, the parameterizing maps don't have to be definable, do they? It's
No.
the number that matters, is not what they.
Yeah, so it doesn't matter that they are definable. So the point is, I think in all the CR parameterization results that I put on the blackboard, they are all definable in the same minimal structure. But for the mild ones, you need exponentiation. So they all use this map e to the 1 over x. So okay. That's where it's a infinitely flat function. So you need at least Rx to make them definable.
But they are known to be definable in Rx or Rnx. Something.
Yeah, they're all definable in Rnx.
Okay.
That's right.
I don't know.
Okay.
No. Okay. Thank you very much then. So we'll be back in half an hour or so, more or less.